tous ceux qui sont dans le hall. Bien, si vous voulez bien vous asseoir rapidement, là on va commencer la conférence. Donc on va reprendre cette conférence avec les deux derniers orateurs de la matinée. On va accueillir d'abord Michal Valko, qui est ici présent et qui va nous donner une conférence sur l'apprentissage avec du bootstrap, les problèmes de représentation et d'apprentissage par renforcement. Donc, pour présenter Michal, il a obtenu sa thèse en 2011 à l'Université de Pittsburgh. Il est actuellement chercheur en apprentissage automatique, machine learning, à DeepMind à Paris, et en même temps chercheur titulaire à l'Inria de Paris. Il est enseignant dans le master MVA de l'École normale supérieure de Paris également. Donc voilà, merci Michel pour cette conférence.
Hello, everyone. Thanks for having me. Thank you, Eric and Mohammed, for inviting me. And I'll thank also the whole team that organized such an nice event. For me, it's also second time in Africa. First time I did vacation in Tanzania. I did hitchhiking, and this is my second time. So I don't know Africa at all. I'm happy to discover it. Today, I think I'm too tall to fit in the frame, so maybe I can go down a little bit. Today I'll talk about a paradigm that we started in DeepMind about 4 years ago. Ah oui, je n'ai pas trop. Yeah. I'm not allowed to have bottles here, so I'll talk about the paradigm that we started 4 years ago called learning by bootstrapping. And I'll describe how this is applied for semi-supervised learning, for reinforcement learning, for learning world models, and what do we do now with it. So this is a very long journey that we have, and involves a lot of people. So I want to acknowledge a lot of my collaborators and the work I'll present. It's a subset of these collaborators that I mentioned on the slide. All right, I think I'll try to figure out how this works. Thank you. I'm not very technically savvy.
Proceed.
Okay, this is next. Oh yes, okay. All right, so I worked in DeepMind, and the quest of DeepMind is to create AGI, right? And we need to get there. We need to several steps to get there. Yes. All right. And so for AGI, we want agents that will generalize significantly beyond the specific tasks that we were trained on. So this is what we would like to have. This is what we don't have yet. And we also, as Jan said, we have very cold reality check, right? We have very limited supervision. Human labels, human rewards are expensive to have. On the other side, supervised learning is what machine learning is good at, right? So how we kind of find a compromise between the two. And so one of the compromises Jan alluded is to master self-supervised learning, and this will hopefully keep agents with stronger generation capabilities to get us closer to this AGI. All right, so what is the agenda? I think I get my dates wrong for 26 and 27, for today and for tomorrow. I will first motivate reinforcement learning. What is it? Why we should work on it now? What are the challenges for it? Then I'll talk about self-supervised learning, and it's a super important part that we'll try to leverage in reinforcement learning. So I'll describe our paradigm called BYOL, then how we also applied it to graphs, to neural data, to videos. And then we go back to reinforcement learning. This is actually what we started from at the beginning. That's what we want to create. We want to train agents that will be able to do something interesting without a lot of supervision, right? Like what we eventually want in our teams, in the DeepMind Paris, DeepMind London, the people I work with, is to create something like agents that will be like a little scientist, that would exactly do this kind of experiment that Jan did. What happens if I leave one side of the paper down? And it would kind of ask these what-if questions. What happens? It's something that we do naturally as humans, but some things that our artificial intelligence don't do yet. Right, so we'll go back to the world models. I'll talk about how we can use them for exploration, or how we could use exploration to create them. We'll talk about interesting motivation, and we present our most recent work on this BioExplore, and some follow-ups that are in the works right now. BioHandsign, we shed some light on the theory, and so on. All right, I think I normally should finish in 20 minutes, but maybe I'll take slightly longer for that. If you have questions, please shout or save them until the end if you want. All right, so what is, in a nutshell, reinforcement learning? Reinforcement learning is something that is learning by trial and error, but in the environment that we don't exactly know how it works. So it's acting, so reinforcement learning also produces learning to act. So we learn actions, we learn policies, what should we do in certain situations in an unknown, potentially stochastic environment, and we usually have some goal that is to maximize some reward. So for example, one good example of this is that we want to learn how to bike without perfect knowledge of physics, right? So, somebody gives us bikes, doesn't tell us how the physics works, and we try to find a way how do we get from A to B. I'll get some water if I'm allowed. All right. So why this is not ready? So reinforcement learning is pretty old as a paradigm. Maybe first inceptions of it was in 50s and 60s. There is some links with neuroscience and so on. But why, after so many years, we have not come to the fruitful solution that we're happy with reinforcement learning that we have now? So reinforcement learning is really, really hard because we need to reason first about time. Things happen in sequence. We need to reason in the long-term consequences of the actions, right? Like, for example, to arrive here, I need to predict, if I have time, take the plane, what happens if I arrived here, how do I get from the airport here, and so on. I need to predict future, what happens if I go beyond the door. I need to actively gather experience. For example, I want a coffee, I could ask somebody, or I could randomly try one of the doors. And also I need to deal with uncertainty. Words changes all the time, and it's difficult to adapt to it. So we will not try to address all of that today and tomorrow. We'll focus on these two that I'm highlighting. So why we would like to do RL now? So as of 5 years, there have been some interesting ground truths that were done in DeepMind and elsewhere. One of them was, almost everybody knows the AlphaGo at the beginning that was able to discover this move 37, and that was playing better than humans. And as a next step, it was AlphaZero, then even next step that let's know it's called Mu0 and PO0, and we have follow-ups of that too. They differ in somehow how much or how little it's needed to give to the system to know. For example, at the beginning, we may not give the game even the rules and let the system learns its dynamics. And as we keep playing with very, very big number of steps, we are able to get better than existing AIs and sometimes even best humans for some games. Another the breakthrough was AlphaStar. One of the difficulties of here, there's many players. There's different maps. There's a brain of fog. There's you need to trade your multiple agents and need to reason with that. And so now we also have agents that can play Star decently well. Yet another things a few months later, we had the AI that can play, for example, games like Capture the Flags using the self-play. And as you can see, one of the difficulty of this is that the only thing you can see is not the full map, but just only first-person view of the play. But in DeepMind, we don't really care about playing some kind of video games and so on. We would like to have one single learning algorithm to solve them all. Right, so the games are easy test bed because we can simulate an environment, we can run a lot of simulation a lot of times. But ideally, would like to have games that can play all Atari games, all first-person views, all physics environments as a controls views, robotics, and so on. So that's our goal. I would like to have somehow even single agent that is able to play them all. All right, so how do we get there, and how one of the motivations that we will try to fuel today, we'll take this the paradigm of bootstrapping of latents that we work in, and try to address that in the next 2 days. So first, I'll talk a little bit about the basics of reinforcement learning, just to set up the ground for here. Then we'll try to introduce our paradigm for self-supervised learning, first for vision, then for graphs, and so on. And then later we applied these paradigms to our, let's say, original problem of self-supervised exploration. Have agents that will do something interesting, intelligent, without any rewards. And we have a suite of our newer algorithms called BioExplorer, Hindsight, and so on that I'll present probably tomorrow. All right, so let's start with the basic oral concepts. So reinforcement learning is is a paradigm, is a set of it's a setting which is interactive, and this is something that I'm excited the most in my research, is to have some kind of closed feedback loops, right? Like in a lot of supervised learning, you have this static data, right? Like whatever you do, what your prediction do, is not creating the next state. In reinforcement learning, what's one of the things that's different, you're creating your data set. If you tell your robot turn left, then the vision field that you have depends on your actions. And so you're creating your data. This creates very intricate statistical dependencies that we like to study, and we have some work with Eric also on that too. That's not IID. So this is something that I'm particularly, as a researcher, very excited about to study. And so this is one of such settings when you have closed feedback loops, and this is called reinforcement learning. So you have agent. This is something that you like to construct that gets some observations from the world. So you have some whatever vision or sensors, and it's able to effectuate some kind of action. So we say that we're learning a policy. So it depends on this observation that agent sees. It takes an action. So, for example, it could be stochastic policy. It takes the stochastic policies from a distribution, and this oftentimes parameterized because it's not easy to enumerate all the actions. Oftentimes, these days with deep nets, then we effectuate this action environment, and we get some reward. And so this reward depends on the action we took, observation before and after. And then we get the next observation. Usually we model them, as the probability distribution of observation, given the action and observation before, in this kind of Markov fashion. More practically, when we implement that, we usually have environments. We have the function called step, that we do step environments. We get to the new observation and action. We have some kind of actor that runs on one machine, and it has a policy, and giving the observation it can output. And what we're trying to do in this feedback loop all the time is trying to make a good decision by learning from experience. So one of the things that we need for such a setup, but one, this is a culprit, it's the rewards, right? There could be extrinsic, so we can have humans that decide that, or we can encode that. That could be, for example, win the game, get the maximum score, clean up the room, whatever, predict the correct sentence. But these are very hard to code, they're very expensive, and we don't have a lot of them. So this is one of the difficulties of reinforcement learning, that we don't that it's not easy to assemble as enough information that would be needed to be super efficient in learning what we need. And so that there is another option, and this is something like human function, right? Like, when you wake up, when you go for a coffee, nobody tells you, okay, you woke up at the time +1, you get the coffee, you had like very fat food, -10, and so on. You have some kind of intrinsic reward that you follow. And so this is something that we try to somehow implant in our agents for this to work. So this could be social, this could be empowerment, desire to control, curiosity. This is something that I've been working on, and this is something that we'll talk about tomorrow. Curiosity-driven exploration. Have these agents to be curious about the world. Have these agents as little scientists, as little children, to try things, break things, and see how the things works. There's losses with meta learning, explanation, and so on. But this is something that allows us also to create some kind of signal for our models without explicit supervision. And so it makes them closer to the data abundant regime of self-supervised learning. All right, so one example, just to be concrete, what is, for example, what reinforcement learning we can apply. Let's say take the old game of Tetris. Then here the state of the game, here it's the same as observation, is a current board and the next block that we have to add. The action that we take, we can rotate this block or we can drop it. when we think it relatively well. The reward what we get is our increment of the score. Here is very simple. And the transition is just the new board and the randomness of the block that we received. One of the difficulty that we face that the large space, possible blocks that could be already in place and possible new blocks that come and all the levels is just too huge, to enumerate and to reason, as a state by state. And therefore, to the rescue, we have function approximation where we can model large scale spaces, with smaller number of parameters. And so in particular, deep reinforcement learning uses deep nets as policies. For example, the simple case, we would just have an observation, we feed it to some convolutional network, we stack some of convolution, then we have a full connected block, and then we have some kind of MLP at the end to predict an action. But the deep nets are not only used for representing policies, but it could also be used, and we will use them next in representing the world. And so the paradigm that we created for this is actually in learning world models, or learning world discovery models, as we call them sometimes, in actually represent the world and learn about it. And so for that we'll now start with smaller example, not as challenging reinforcement learning as a vision, and describe self-supervised learning method that we use in our research. So first of all, why do we need self-supervised learning? In a computer vision, the goal is to process some image and to solve then downstream tasks, as examples that you can see in Jan's talk before, such as classification, segmentation, or depth and estimation. And so in particular, in the vision, this model is a specific kind of deep network that we have. And so we pass the image to encoder, and then we, on top of the encoder, which is somehow able to encode the image into some kind of latent space, and we then later put additional, let's say, MLP, a multi-layer perceptron, for training downstream task. For if you want to do, for example, segmentation, we train a network specifically only that part, just to do segmentation in latent space, because we believe it'll be easier to train the small network in the latent space than the original pixel space. And so the question is how to actually we train this encoder, how from the image we find some representation in the image. So this is the goal for next, let's say 10 minutes. Later, we'll try to see how to use encoder to represent not only the image, but all the past history of interactions. So how to somehow have the memory and some kind of representation of what's going on and what happened before. So, a motivation for our, I think I also had the one slide before that. So for all of this, we need to, get some data, and in practice there exist two kinds of data, right? Like on one side we have this label data where each image comes with some kind of ground truth. For example, we have a dog and we have a label of the dog, or particular squares, or even better shapes where things are in a specific term. On the other side, we have lots of unlabeled data, that we did not have to ask human to train, right? And so the goal of self-supervising is to leverage this unlabeled free data that comes for free, right? So how do we actually will do those things? So first, we use this immense amount of labeled, cheap, unlabeled data. So we have we train a generic encoder, generic in a sense that we will be able to use it for any task after. And then in a downstream networks with labeled data, in a classical supervised fashion, we only need few labeled data to train these small ping networks to achieve specific tasks. So in this presentation, now I present BYOL, which is one of many particular ways to train this encoder. And so the output of this method is a particular encoder that can take, for example, some image and input, let's say 248 numbers that would represent this image. So this is our goal. And so, which is called BYOL, and I explain why it's called. So the intuition and the main ingredients of many self-supervised methods is to take the advantage of image transformation, right? For instance, we take an image of the dog and we transform it with random crops or with distortion or something else. Then core information, stays in the picture. So we can expect this high-level semantic information to be preserved by simple transformation. One thing that also nice to notice is that, okay, well, it's not only dog that's in a picture, right? It's also the grass, right? So when we apply this transformation, let's say all of these other things are preserved. So we're no longer only trained to represent, we don't want our representation to have some kind of one-hot coding that's a dog. We would have to some kind of continuous representation that, that's representing all of the image. And so self-supervised learning methods also kind of aim us to not represent particular things in the image, but kind of ensemble of this image that we have. All right, and so BYOL, as many other self-supervised learning methods, builds upon this idea, and specifically given a transformed view of the image, we try directly to predict another transformed view of this image with some additional information. So again, as both views contain the same semantic information, we should be able to predict representation independent of the transformation. Simply said, transformation of the dog is always a dog. All right. So how does this work? So in particular, we process this first view with an encoder that is followed by some predictor that enable us to do this prediction. Let's say a multi-layer perceptron, one or two layer perceptron. And, but imagine that we are also dealing with unlabeled data, right? So we don't really have, something that tells us what is on the image. So we need to, predict, but we need to regress this information to something. And so therefore, we train the other encoder that will be some kind of older version of the previous one to create some kind of the target, right? So first, we only train the network mapping, making the prediction, but we do not propagate this information back to it, right? So it's important that, the only thing that's being trained here at this stage is only in the encoder, and we use only this bottom network that we call the target network just to create a target. This is very important to know and to notice, because we don't want this encourage the views to be easily predictable. Because, for example, if all the networks, output 0, then you can predict 0 from 0, and that's trivial, and this is not what we want. We want to have some kind of meaningful information. So rather, we want to force the views to be predictive of each other. And so in second, in BIO, both prediction and the target, are continuous. So we're not predicting, any specific label, and therefore we use L2 loss to predict them. So if we do it this way, kind of interesting phenomenon that happens. So at the beginning we have nothing, right? So what we do, we need to, start with this encoder with some kind of random weight. So this is important to notice. We have random weights, but doesn't mean that we're predicting a random target. That would not be meaningful. But if we already, use random weights, an interesting phenomenon will happen. So beginning of the training, we have this, we initialize 2 networks with random weights, but when we start to regressing the predictor and the randomly initialized encoder towards this target. And so if we do so, then we have this interesting phenomenon that even if we keep the target fixed to a randomly initial network, this process already allows the encoder to be better than initially started. let's say, like in some metric that I'll describe, like at the beginning, we have, let's say, 0% accuracy. Now we have 1.7% accuracy after this process. It's not good, but it's better. Well, what we do next, we then have this natural idea that we can copy the improved trained random initialize encoder, and it got stronger, right? We improved its efficiency by a little bit, but since we have stronger encoder, we can copy this encoder to our targets, and instead of randomly initialized network that produce roughly random targets, we get better targets. Not perfect targets, but better targets. Once we have these better targets, we can train better encoder, right? We can generate even higher quality targets, right? So our encoder gets stronger even more. And so, as you can see where this is going, and that's why we call the method bootstrapping. We go from encoder to even stronger encoder. We regress the targets, stronger things are better. We regress them again, even better, and we iterate this process until convergence. So this is, and in the end, we output, our network, and we see how it goes. However, like this, there has been life before this existed. Self-supervised learning method exists, for some time, and before, this is the line is happened until roughly 2020, June 2020, when we released our methods. Most of the methods were not doing it this way. There were either, generative methods that were trying to, generate images directly in a pixel space, or the best methods, prior to this, were contrastive. All the ideas were kind of there, but the best performing methods that existed were contrastive methods. So a little bit about this contrastive method. They have a very similar architecture as the stuff that I presented. So you have some kind of two set of networks, they call like these Siamese architectures. And then, you try to look at the latent representations of the networks. And what you were trying to get, you will try to push like representation of similar images closer to each other and dissimilar images away from each other. So this is something that worked the best. The difference that we brought in our fields that we didn't need to have these negative examples. And there's multiple reasons why this is good. So first of all, there's a conceptual difference, right? So we don't actually need to define node and object. So for the node, not a dog, for example, if you had this image of the dog, we had to some kind of define what is not a dog. First, you don't know anything because nobody labeled you any data. So you probably try to pick a random image and say, okay, well, it's probably not a dog. But this is actually difficult. For some domains, it's difficult to say what is not an image. And you could be wrong, because if you put random images, it could be a dog, right? So you kind of encode also mistakes by doing this. Another important thing is scalability. For this non-object, we needed large batches. Usually this training happens by batches. And for making contrasting method work, you need to have large batches. In Bio can work with super small batches of 2 or 16, which is not true for contrastive method. But particular, where you really feel that this scalability is super important is graphs. In graphs, for example, in things like Google Maps, you try to embed every single node, into some latent space. And one way to decide what is not a node, you take another node. Well, the thing is that for graphs, for these methods, for this contrasting method to work well, you need to, kind of do every node for each other. And this is, almost quadratic quadratic time and space complexity. And so, this is not perfect. You can downsamples, but this doesn't work well. What is beautiful about this approach that you don't need this, quadratic thing, and you actually keep kind of linear in the number of nodes that you're embedding. And the final thing why this removal of negatives, there was a whole industry of research that was about how to create good negatives, and by by bringing this, we kind of managed to not need that. Is that we are robust to augmentation and bad size. There was a question on adversarial attacks. The more robust you are to this, more robust you can get, not completely robust, but more robust to adversarial attacks. All right, so let's talk about performance of the build. First, how to actually evaluate the things that we don't know, we don't have any labels. So one standard evaluation in the field is that we first train this representation, which is a network, that gives us, it takes the image and outputs some latent representation. Here it's a RANSNet. We freeze the representation, so we will not update this weight. Then we add linear layer on top of it, and we only train this linear layer with few examples on specific tasks. For example, classification on ImageNet. And so, at the time of release of our method, this was a performance of supervised learning method to how to achieve this classification of ImageNet. And so these were the best performing methods for self-supervised learning. There's Moco, SimClear, super famous, and there was still some gap between supervised and self-supervised methods. And the best performing methods were indeed contrastive, as you say, SimClear for 2x and 4x. And the method that we brought, kind of provided a small revolution in this field that now no longer, people aim for getting best performance with contrastive method, but they are doing now non-contrastive or predictive methods, depending how you would like to call it. And at the times of submission, we were matching the gap or bringing it as close to gaps as we could to this supervised learning method. Actually, it's maybe a little misleading to actually say that, okay, supervised learning method are like the best possibility you could get. You could actually can get better, and in some kind of graph or graph data sets, we get better than supervised learning methods. So how is this possible? How you can get better than supervised? Well, the thing is that, in the labels that human provide, you could actually even have mistakes. So self-supervised learning methods, that, kind of are somehow less robust to these mistakes in human labeling, you could potentially, come up with a better encoder as the one that you would get by labeling and by propagating the human labels. Yes, all right. So let's highlight the key ingredients of our methods to remember them, because we will use them later for reinforcement learning. So what do we need to have to make this work? We need to have some kind of image transformation. These are super critical, and this is quite almost cheating to call it self-supervised, because very smart humans over the decades designed the transformation of the images that are particularly good, and that they preserve semantics and produce new things. For example, in our method, we didn't at all even focus on trying to get the new augmentations. We take the ones that were on the state of the art, which was SimClear from the team of James Hinton, and we used exactly the same. Then there's a thing that you don't want to transform only one time, but only several times. You want to apply 3 or 4 of these transformations. And in particular, what we do, we apply all of this transformation with some probabilities. We tune these probabilities. It's a very important thing to tune well. But I'm just want to highlighting that to make it fully self-supervised, you would not even need these smart humans that design transformation. But this is actually the human knowledge that do is. You kind of distill the human knowledge instead of doing labels to create a nice transformation. The hope is that it took less time to design transformations than create labels. The second thing to make BIOL work is the, I think it was a stop gradient. Yeah, it's a target network, to produce labels, and additional predictor on online network. Why this method did cause this small revolution, as I mentioned, has a very simple training procedure. There's no negative examples. That was a big drawback of contrasting method, and also works on the embedding level. So there's no particular pseudo labels that exist in our methods. I'll go a little fast over this method, but importance of creating a good encoder is not that you can just classify, that you can do many things. And so to convince people that this is by this method you get encoder that's more universally applicable, we had to do like benchmarks on all of the methods that are that are required in the field. For example, semantic segmentation, depth estimation, which all have a mean intersection over union, average prediction of 50. There's each of the fields have their own metrics, and we show that our methods is able to improve all the metrics. But to nail down this more comparison with SimClear, because it's also interesting to compare why we don't need these negative examples. Both of them do semi-supervised learning ImageNet, and we also try to do different benchmarks. So let's pick up some interesting comparison. First, you would like to have as least human supervision as possible, right? Like this is somehow the goals that we will trying to have, in AI research, to reduce amount of the humans that need to train the data, that it could be useful, right? That's why we'll try to put as much as possible, self-supervised learning and reinforcement learning to reduce the need for human labeling, because in this interaction is very slow. And so one way of reducing, well, for example, here human input in such method is reduce the number of augmentations that you need to have. And so, for example, this is a plot that if you remove some kind of augmentation, we see that our method, of course, decreases performance, but it decreases performance much less than, for example, SimClear, which is maybe more sensitive to particular augmentations. And another thing that's important, practical things, is also less sensitive to the batch size. Of course, always bigger batch sizes are better, but in BIOL, when we reduce the batch size, our method degrades less than contrasting methods before. All right, let's try to shed some intuitions, which is still very much ongoing work. It's still not completely understood how things work. There is many ongoing research going on in our side, in the young groups. There is Grégoire Mialon, Kentan, they do a lot of work on this field. Why and where, what's the relation, what's the link between contrasting and non-contrasting? These are some kind of intuitions that I'll try to provide. So first, one of the difficulties and one of the first drawbacks, when we presented these methods, for example, to Jeff Hinton, was like, why this thing doesn't collapse? Because there is a very trivial solution to this loss is just some kind of constant representation. If every encoder gives you constant, then the loss is 0. You can predict perfectly this constant, and this optimal solution, right? So let's look at the loss that we have. First, what we're trying to have, Q is the output of the predictor on Z theta of latent representation. Z Xi is the latent representation of the target network. So our loss is just simple L2 loss. Since we normalize the targets, it's also you can be expressed as a cosine similarity loss. So this loss has trivial global minima, but it doesn't achieve it somehow empirically. So why this might be the truth? First, we don't really optimize the targets by gradient descent. We do this empirical exponential moving average of the thing. So we ideally what we would like to have, but we don't do for practical reason. We would keep all the networks that we have in the past, and we would average them. This is something that that provides stable targets. This idea of these moving targets, since we are reinforcement learning researcher, mostly we borrow from DQN, which similar thing is done to stabilize the targets. Why we actually care about stabilizing targets? Because neural networks are good of predicting non-moving labels. And so the more things is stable, the better we can improve our learning. But at the same time, you don't want to have a completely stable and movable targets because you want to have a better targets, right? So this is some kind of so ideally, or maybe theoretically, best will be take all possible networks if you train and do average of the labels. First, you cannot do that. That's infeasible. You would not. It's very difficult to average the labels. So instead, we average the weights because that way we don't need to store it. Then also we don't want to store all the networks that we had in the past. So instead we do some kind of cheap approximation of that. We take the network before, we multiply it with 1 minus eta, and we add the current network. So we kind of only need to keep 2 networks in the memory, one online, one target, and then when we replace the target, we just do the mixture of that. So what's important to notice here, that by doing this EMA update, it's different than doing the gradient descent on the loss of the bile, right? So the loss of the bile will be just, take the derivative with respect to the parameters and move the parameters of target net. We don't do that. We do this EMA update, which is different than gradient. And so bile is not optimizing the loss that is optimizing. Just to make clear what I'm saying, we do step of the gradient, for the online network. For the target network, we do this EMA, and then, since the network changes, there is no particular loss that bile is optimizing, and therefore it's less likely, that you can just, you can say, okay, well, this naturally does gradient descent to the particular solution. That's first anti-Michal, right? And so it's still true, even in this explanation, that a constant representation, minimizes the loss, and there's some kind of equilibrium of these dynamics that we'll study tomorrow. But these dynamics may not be stable. Maybe you can reach and go away, or maybe not attractive as a dynamical system. So to give slightly more intuition, is like, we could, there are 3-4 elements that make bile work, and we try to look of which factors prevent collapsing, right? So if we, for example, remove predictor, bile collapses. If we remove this update, so we just always keep the same random initialization, but keep the stop gradient, so we don't trade it, this barely learns. So there's one remark, like bile without predictor is another existing method called mean teacher that existed but used also supervised learning. We can also add explicit negative example to see how much it improves. It improves tiny bit. So we also were interested to see some kind of what is in between the contrastive method, for example, SimClear, that puts closer examples together and further example far away, and bile. So it's kind of try to find something in between, some mixture of 2 methods. So you can take loss of the bile, what you say on the right, some beta, some contrastive method. And then you can see all the combinations that are between contrastive method, this particular SimClear, and bile. For example, you can have predictor or not. You can remove target network or not. You can, you can add this negative example of not. And so there are 3 differences between bile and contrastive methods. Are this one, we have predictor, we have target networks, and we have no negative pair, right? This is our first line. And SimClear, doesn't have, it's different, all of this. But there is everything in between, There's methods, that collapse, you can see them on both. There are methods that does slightly worse, and there are methods, there are new methods that exist. For example, the one line out under the SimClear with 469.9 that uses predictor, but doesn't use target network, was later replicated as a SimSiam network. And so there's other networks that you can use, but we still, given that we still prefer what we have now, also for reinforcement learning purposes that I'll describe tomorrow, because this is the simplest. We don't need to have these negative examples, and at the same time you have simple method that you can just train first by gradient descent. We use Lars. and the EMA target update. All right. So another thing that we'll try to understand that, what is the role of this predictor, right? Would it even work without target network? And so like one experiment that we did, we tried to not use EMA update, so remove this target network and see if this is really crucial for that. And so the one way that we had this kind of hunch that what is important, we not only hunch, but we also saw then experimentally, that was very important that this predictor was kind of near optimal. And so one way how you can make the predictor more optimal, you can actually you can simulate it by doing different learning rates on a predictor. And so these are different learning rates. This is multiples of learning rates of everything else. So one is for example the classical bio, but now without target network doesn't learn very well. It's 5.5. But on the level of let's say 10. If the maybe optimal thing is optimal thing was 10, if the predictor learning rate was 10 times faster, so that means it has time to become kind of near optimal for the current data it has. It was almost able to recuperate the full power of BIOL, right? It's not 70, 62. But that 66 sorry, but that showed us that one of the roles of predictor is to one of the role of target network is to keep predictor optimal, and so keeping this near optimal predictor is a key for using it. So let's say slightly more theoretically, what this optimal predictor is doing, let's call him Q star for the latent Z, it's just expectations of the perfect one will give you expectation of the target labels given the online network, right? And our loss, you can rewrite the loss. We don't have time to do that. Very simply, it's actually the variance of the target outputs given the online outputs, online latent representation. And so there's two ways. And so loss is you're trying to decrease, so which is completely equivalent to decrease the variance of the latent labels. But there are two ways to decrease variance. First, you decrease, for any conditional variance, there's two ways to decrease. Either you decrease what you condition on, or you increase what you condition on. So one trivial way is to decrease, the things that you condition, and this is equal to collapse representation. Variance of the constants given anything is equal to 0. So one way to find the minimum is to just set the Z targets to constant label, and this gives this indeed optimized loss. The second way, and this is what we believe BIOL is doing, it's increasing the information on this online projection. So by giving more transformation, more augmentation, we increase information that it gives online prediction, and this we believe this is doing. And since we have this EMN update, we have more somehow empirical evidence, not a proof, not a complete proof. There are some proof for simplified versions, but what we're seeing is happening. We increase this variability of online prediction. All right, so I have roughly 10 minutes. I'll just describe some other application of these things, and so we can focus tomorrow purely on reinforcement learning setup. So we were not only interested in images. This was kind of at the beginning as a side project. We're always interested in representing sequences and replacing world models. So we did some extensions of BIOL. In particular, this was asked from Google to, for example, find representations of the graphs. So very similarly, you can take as an image, you process it by some convolutional network. Here, for example, you can do this encoder by graph convolutional network. Also, you can have more fancier graph attention networks, so like kind of transformers equivalent in a graph setting. Here, the transformation could be very simple, adding or removal of the edges. And then you try to, at the end, just, do the same thing, predict the representation of one node given another augmentation of the same node. Exactly the same area applied to graphs. What's amazing here that that this method in the graph setting, the best performed methods until then were also contrastive. By these methods, you don't need to create these negative examples, and so you're able to scale it, to billion, for example, edges. And so we entered the competition last year, 2 years ago now, 2022, June 2022, used this method, and it was able to process, 400 million nodes and 1 billion of edges, because it didn't need to, do these negative examples. And DeepMind was one of the top three methods. So what is nice that this kind of simple solution works even 1,000 times larger data that was previously possible with kind of method. All right. And another thing that we try to measure is it's a performance on protein-protein interaction. This is how you can also find encoders that will code particular nodes in the protein. So here we use graph attention networks, and there is a way of the better. I mean, one of the metrics that you look at that is entropy. So better entropy of the labels is better, and so we were able to improve this over the other contrastive methods. Next thing that the reply is to neural signals, because this is another sequential signals. So we slightly modify the architecture of BYOL, and instead of just doing, because it's also very difficult to, what are the different, let's say, transformations, because here you have just one. These are readings from monkeys. This is collaboration with Georgia Tech. They have 8 monkeys. They have their names, and they make them different tasks, and then they want to try to do some kind of embeddings better than PCA for this task, right? So here what we'll try to see is what are the different modification of the pairs, and these are somehow what are these kind of similar examples that we can do. Augmentation, because one, we can do augmentations in before, there's some kind of crops, we do that, but we found that it improves that if we add some additional augmentation of similar close by in time, these are the blue segments of the examples, as additional augmentation, because they probably correspond also to the same thing. But adding them directly as the close by example didn't work, so we kind of created cascaded BIOL that we added one predictor on top of that was also asked to predict these other, let's say, auxiliary augmentations. Just a little bit about that. And finally, getting closer to reinforcement learning, we apply BIOL to videos. And so here the idea was to take long videos, and we have kind of the bigger view, what do we call broad view, and the narrow view, which is just like kind of few milliseconds of some kind of action. And what we are trying to do, we try to, from the broad view, you try to predict the narrow view, and vice versa. So we have a narrow view on one side, broad view on the other side, and that we kind of have this kind of similar predictor on both of networks. One predicts broad view to the narrow view, and one narrow view to the broad view. So there are different encoders and different predictors, one called F and one called G, and you predict to each other, and by that way you can improve what was able to exist in video embeddings. And it also nice thing about this kind of double architecture, we can actually have some different modalities, for example, audio or some kind of the visual rasterization of the moving the targets. All right, and so this is what we have for the kind of introduction of the paradigms, and in tomorrow, in the continuous tomorrow, we will go back to the reinforcement learning, and we try to see how we can actually apply this BYOL, this paradigm for representation, to the reinforcement learning setting when you have visually complex environment and you don't have somehow any rewards, and you'd like to see something interesting. So we use this as a framework that we learned today, and we apply this to reinforcement learning and create some kind of self-supervised learning signal to find good representations, and then use this representation to guide our policy and action. So thank you very much. About like bially secretly contrastive, and we had a lot of talks to them, and like at the end, like we were not able to demonstrate the results that they showed. But no, I don't think because to answer to this more scientifically, we wrote another paper called "Bile Works Without Batch Norm," and so I invite you to read it. When we kind of remove the batch norm with some different initialization WS tricks, that was able to achieve the same result. Yes, but there is some things. Jan has a paper on like making kind of equivalence of contrastive, non-contrastive learning in a different way than a batch norm. That's another way. But at least there is no evidence that the batch norm is secretly contrastive thing in bio. Thank you.
Alors notre dernier intervenant ce matin est Redha Moulla, qui va nous parler d'intelligence artificielle et de business. Donc juste une présentation de Redha le temps qu'il arrive. Il a réalisé une thèse en automatique à l'Université de Lyon en France. Maintenant, il est consultant en intelligence artificielle et fondateur de AxIA. Et depuis une dizaine d'années, il travaille pour des entreprises. Il aide les entreprises dans le secteur de l'innovation et des transformations en se basant sur les données. Il est aussi prof, enseignant en deep learning à l'EPITA, une école d'informatique à Paris, et aussi, on a la chance, à notre école centrale à Casablanca.
Bonjour tout le monde. Je suis ravi moi aussi d'être ici, comme mes trois prédécesseurs. Je vais essayer, je suis désolé, je suis un peu mitouflé parce que j'ai attrapé un peu froid. Je vais faire la présentation en français, je vais essayer d'aller un peu vite pour qu'on aille tout simplement déjeuner. Donc, je ne sais pas du tout comment ça fonctionne. Ça marche. Ça ne marche pas. Visiblement, il n'y a pas que moi qui ai un problème. Quelque chose à faire? J'appuie sur quoi? Ah, c'est celui-là? Ah bah oui, très bien. Donc, je vais vous parler, moi, de mon point de vue donc, de l'intelligence artificielle dans le business. Il faut entendre par là l'intelligence artificielle en entreprise, tout simplement. Donc, il y a des personnes qui ont parlé très brillamment de l'intelligence artificielle du point de vue de la recherche, du laboratoire. Et il y a des gens qui travaillent sur l'intelligence artificielle du point de vue de l'impact de l'intelligence artificielle sur la société, qui est intéressant également. C'est toute une discipline de recherche. Mais il y a l'interface entre les deux mondes, le laboratoire et la société, qui est tout simplement l'entreprise. Et donc, c'est intéressant aussi de regarder peut-être ce qui se passe à l'intérieur de l'entreprise, quels sont les défis, quelles sont les contraintes et les opportunités potentiellement pour innover. Donc, je vais essayer de parler de cela d'une manière relativement bref. Je ne vais pas aborder tous les points. Donc, gros, je ne vais pas vous surprendre si je vous dis que toutes les entreprises ne sont pas logées à la même enseigne et du point de vue de l'adoption de l'intelligence artificielle. Il y a des entreprises beaucoup plus matures que d'autres, qui ont atteint une maturité plus avancée, même pour certaines. Donc, j'ai un peu, de mon point de vue, divisé cela en 3 classes, une sorte de taxonomie là qui n'engage que moi. Donc, il y a les entreprises que j'ai mises un peu dans la première classe, donc qui font ce que je peux appeler de la décision d'une manière très très générale, hein, qui sont au stade de la BI, de la statistique, de l'analytique, un peu d'optimisation, etc. Ce qui marche très très bien d'ailleurs. Il n'y a pas d'injonction nécessairement à faire du machine learning. La plupart des entreprises sont à peu près au 2e stade de l'automatisation des process. Hein. Tout simplement, ça s'appelle l'automatisation d'un ciblage marketing, l'automatisation de la modération sur un réseau social, etc. Il y a quelques entreprises qui sont beaucoup plus avancées, qui utilisent l'intelligence artificielle réellement, véritablement pour innover, pour créer une nouvelle offre, un nouveau business model, etc. Soit des pure players comme vous connaissez tous, hein, comme OpenAI, DeepMind, etc. Mais on peut trouver aussi certaines entreprises qui ne sont pas a priori spécialisées dans l'intelligence artificielle, ni même dans la technologie, mais qui sont devenues, d'une manière ou d'une autre, des entreprises très très tech et très axées sur l'intelligence artificielle. Il y a un célèbre fabricant de chaussures de sport, etc. Donc, les défis de l'intelligence artificielle en entreprise, je les ai un peu listés en 4 catégories. Donc, il y a le défi culturel, il y a un défi qui est lié aux données, puis il y a le défi technique, il y a un défi qui est nécessairement organisationnel parce qu'il faut bien s'organiser pour innover d'une manière générale et spécifiquement pour faire de l'intelligence artificielle. Donc, pour le défi culturel, hein, c'est un peu souvent le premier frein pour l'adoption de l'intelligence artificielle. Hein, ça concerne le top management. Les managers, quand on discute avec eux, il y a toujours, souvent, 2 attitudes qui sont un peu opposées, qui sont un peu extrêmes, hein, d'ailleurs. Et il y a le manager qui va dire, qu'est-ce que vous voulez que je fasse avec de l'IA? Moi, je ne suis pas du tout une entreprise techno, ou alors je suis techno, mais je maîtrise ma technologie, je n'ai pas besoin a priori de l'IA. C'est un saut dans l'inconnu pour lui, donc il ne veut pas du tout aller vers l'IA, quoi. Il y a le manager qui est peut-être un peu plus curieux, plus enthousiaste, et qui va dire, l'IA, bien sûr, j'y vais, ça va changer ma vie, ça va créer de la valeur tout de suite. C'est un piège également parce qu'en général, il y a le data scientist qui arrive le matin, on lui donne les données, l'après-midi, il va passer, il va lui dire « Vous avez trouvé quoi maintenant? Quels sont les résultats ?» Et le data scientist, le pauvre, il faut bien qu'il dise quelque chose quand même. Donc, c'est deux pièges-là qu'on va rencontrer assez souvent et qui sont en fait aussi des freins en réalité. Il y a le défi qui est lié à la donnée. Donc, souvent, il n'y a pas de données, hein, parfois, hein, ou peu de données. On ne peut pas faire du machine learning, on peut faire d'autres choses, hein. On peut faire un moteur de règles, et c'est très bien, ça peut marcher en attendant de collecter de la data potentiellement, etc. Mais a priori, on ne peut pas faire du machine learning. Et on peut avoir beaucoup de données, mais elles ne sont pas de qualité, et ça, c'est un stade un peu fréquent dans les grands groupes aujourd'hui, hein, c'est ce qu'on va rencontrer le plus souvent. Mais on peut avoir aussi beaucoup de données et qui sont de très très bonne qualité, mais on ne sait pas par où commencer parce que les architectures sont complexes, parce qu'elles sont silotées, etc., etc. Donc il y a aussi un défi qui est très très important, qui est la donnée. Il y a un défi technique, purement technique j'ai envie de dire, hein, qui est lié tout simplement à ce que ça va marcher, à ce que mon modèle de machine learning va marcher. On ne sait pas au stade de la preuve de concept s'il y a un algo qui peut résoudre la tâche qu'on veut cibler, et quand bien même on arriverait à un algorithme qui a des performances très très satisfaisantes, c'est pas sûr qu'on puisse le déployer. Parce qu'il est très complexe, parce que peut-être les bases de données sont silotées, etc., etc. Donc, ce n'est pas un gage de réussite du projet. Et quand bien même il est déployé, etc., il y a ce qu'on appelle le data drift. Donc, les données, donc, elles bougent, hein, donc elles changent en fonction du temps, parce que le monde change, tout simplement. Hein. Et l'exemple le plus probant, c'est le Covid, qui a eu comme effet sur certaines entreprises de disparaître, tout simplement. Donc, ce sont des freins techniques. On va voir, pour le dernier, on sait un peu le régler, mais bon, pas complètement. Il y a un défi organisationnel, hein, donc tout simplement comment s'organiser pour faire de la data science. Aujourd'hui, il n'y a pas de cadre très très clair ou de pratique très très claire comme en informatique. Donc c'est quelque chose qui est un peu en rodage, on va dire. Et les data scientists ne travaillent pas toujours bien avec les développeurs ni avec les métiers. Je vais passer ces slides. C'est pas très intéressant. En revanche, ça c'est intéressant, mais je l'ai passé. Donc je vais essayer de faire un parallèle entre l'IA en industrie, l'IA en entreprise et l'IA en laboratoire. Souvent, ce n'est pas tout à fait la même chose, hein, à part pour certaines entreprises qui ont des laboratoires intégrés, etc. Donc il y a déjà un problème qui est lié... Est-ce qu'il y a un verre d'eau quelque part ou... Excusez-moi. Donc, je disais, il y avait un problème il y a toujours quelques différences entre l'IA au laboratoire et l'IA comme on l'a fait en entreprise. Déjà, du point de vue des données. Les données, parfois, en entreprise, il n'y en a pas tant que ça, elles ne sont pas de bonne qualité, etc. Alors, quand on regarde, moi, par exemple, je travaille sur une solution qui corrige les copies des étudiants en langage naturel. Hein. Je regarde, donc, c'est un sujet de recherche qui existe depuis les années 60, etc. Et quand je regarde des papiers scientifiques, je vois qu'il y a des gens qui entraînent des modèles sur des milliers de copies, potentiellement, pour faire des algorithmes, ils sont satisfaits, etc. Alors que moi, je ne peux pas me permettre d'entraîner sur 1000 copies. Les promotions, il n'y a même pas 1000 personnes, a priori, hein, la plupart du temps. Donc, il y a des considérations un peu liées au réalisme et qu'on va retrouver donc plus de contraintes en entreprise que dans un laboratoire, notamment académique. Il y a aussi quelque chose qui est lié donc aux contraintes de mise en production qu'on ne va pas retrouver quand on fait de l'IA pour le milieu académique. On ne va pas penser vraiment à la mise en production sur AWS ou je ne sais pas quoi. On ne va pas penser à la mémoire de la fonction lambda ou autre chose. Pareil pour les métriques. Hein. Souvent, on ne va pas nécessairement regarder des métriques qui sont liées au métier quand on fait de la recherche dans le milieu académique, alors que quand on est en entreprise, peut-être parfois on va favoriser l'explicabilité au détriment de la performance prédictive. Parfois, on va aller jusqu'à peut-être même un modèle qui a 99% de précision. Bah, si le 1% là où il se trompe ont un coût très très élevé, qui peut être un coût financier ou humain, etc., on ne va pas le déployer. Donc, c'est tout à fait différent. Bon, ça, c'est pas très intéressant. Mais est-ce qu'on peut faire de la R&D en entreprise? Ce que j'entends par là, est-ce qu'on peut faire de la R&D en entreprise ou en dehors, évidemment, des big tech là que vous connaissez tous, hein, qui, bien sûr, font de la R&D, personne n'en doute. Bon, on a eu même la preuve ce matin. Oui, de mon point de vue, parce que certes, tout le monde ne peut pas entraîner des gros modèles de deep learning là dont on a parlé ce matin, mais on peut faire de la R&D sur des problématiques spécifiques au métier, tout simplement, hein, qui peuvent être de la R&D sur des petits échantillons de données. Et là, il y a toute une longue traîne de cas d'usage, hein, donc de sujets R&D, qu'on peut résoudre. J'irai même un peu plus loin en réalité. Je dirais, il n'y a rien qui dit aujourd'hui que l'intelligence artificielle, la vraie intelligence artificielle, hein, ne viendrait pas de cette recherche-là. Parce qu'elle est faite sur des échantillons de données qui sont relativement modestes, etc. etc. Donc, ce n'est pas encore plié, on peut tout à fait faire de la R&D, même quand on n'a pas beaucoup de GPU, etc. Sur les opportunités quand même. Donc voilà, j'ai parlé un peu du data drift là. Donc aujourd'hui, ce qu'on utilise, c'est des approches de type MLOps pour mettre à jour les modèles, donc les données, tout simplement, et entraîner les données. Donc ce sont des choses qui viennent du DevOps, du développement, donc, et qui fonctionnent pas mal, mais ça ne résout pas complètement le problème de data drift. Ça, je vais le zapper quand même. Donc, il y a l'opportunité, là, je vais rejoindre un peu, du coup, Michal et Yann, donc, qui est, pour moi, aussi l'apprentissage autosupervisé, c'est sans doute l'opportunité la plus importante ces dernières années en entreprise. L'événement le plus important ces dernières années en entreprise, c'est clairement l'utilisation extensive du deep learning. Parce qu'il y a des données non structurées qui sont du texte, des images en abondance en entreprise. Et du coup, tout le monde s'est mis à faire du deep learning parce que voilà, on peut extraire des caractéristiques très très intéressantes, même de données non structurées avec du deep learning, c'est fait pour ça. Sauf que le deep learning demande des quantités de données labellisées qui peuvent se compter en millions, potentiellement même plus. Et donc l'apprentissage autosupervisé là est là pour remédier à ce problème, tout simplement. Et du coup, dans le contexte du NLP, parce que c'est de cela qu'on parle, et des transformers en particulier, c'est très très simple de faire aujourd'hui ce qu'on appelle l'apprentissage autosupervisé, donc le self-supervised learning, là, dont parlaient Michal et Yann, qui consiste simplement à terminer une phrase, tout simplement. Je commence une phrase, je vais entraîner l'algorithme pour qu'il la termine, sachant que je connais évidemment la fin de la phrase. Donc, j'entraîne comme ça mon modèle sur des quantités incroyables de données, des milliards de tokens. Il y a une forme d'intelligence qui apparaît, qui en tout cas donne des résultats qui sont assez intéressants. C'est une intelligence encore superficielle, c'est pas vraiment, c'est de la mémoire associative et de l'interpolation. Mais grosso modo, on peut faire pas mal de choses avec ça déjà. J'ai oublié un E à fine-tuning. Donc ces modèles-là qui sont entraînés juste pour prédire le prochain mot, à compléter des phrases, ce qui est intéressant, c'est qu'on peut ensuite les adapter à des tâches. Faire de la classification, de résumé texte, etc., sur le même modèle a priori, qui est entraîné juste pour terminer les phrases, pour prédire le mot suivant. Et ça, c'est un changement de paradigme qui est très, très important, parce qu'avant, quand on parlait de machine learning, quand on parlait de généralisation dans le cadre du machine learning, la généralisation pour nous, c'était vraiment comment aller du training set, les données sur lesquelles on a entraîné l'algorithme, au test set, les données que l'algorithme n'a pas encore vues. Ça, c'est un peu différent, c'est un paradigme complètement autre. Maintenant, la généralisation, c'est comment généraliser avec le même modèle sur plusieurs tâches. Pas seulement aller du train au test. Comment je vais généraliser avec le même modèle sur plusieurs tâches. Donc, c'est un changement très, très important. Autre changement plus important, c'est que si j'entraîne mon modèle sur vraiment beaucoup de données, eh bien, j'ai même pas besoin de faire du fine-tuning, qui nécessite quand même une centaine, quelques centaines, quelques milliers d'exemples, mais je peux lui donner juste que quelques exemples. Ce qu'on appelle donc le few shot learning, là, qui est en réalité qui a émergé avec GPT-3 que vous connaissez tous. Donc, il n'y a pas besoin de réentraîner le modèle, de faire une descente du gradient, etc. Le fine-tuning, c'est quelque chose qui est déjà utilisé en entreprise. Il y a des gens qui déploient des modèles, des BERT fine-tunés pour la classification, pour le routage de mails, etc., et ça marche. Le few shot learning, c'est quelque chose qu'on commence à envisager en entreprise. On travaille sur des cas sur des modèles de type GPT-3 en open source, et c'est quelque chose, je pense, qui va venir, au moins pour une période, peut-être 5 ans, je ne sais pas quoi, qui sera une sorte de norme, je pense, parce qu'il peut résoudre vraiment des problèmes très, très fondamentaux qui sont liées à la disponibilité des données. C'est quelque chose qui, d'après le peu de retours que j'ai pu voir, quand même fonctionne, en tout cas qui est très prometteur. Donc, je vais terminer sur les défis éthiques. On ne peut pas parler d'IA sans parler d'éthique. Donc, est-ce que les décisions vont être sous-traitées complètement à des boîtes noires un jour? Bon, j'ai envie de dire, ça dépendra de nous, pour le coup. Est-ce que l'IA va remplacer les humains en entreprise? Aujourd'hui, on n'a pas vu un remplacement d'une manière significative des humains en entreprise. Ce qu'on commence à voir, c'est peut-être une sorte de remplacement partiel ou potentiellement quelqu'un qui aurait besoin de 5 personnes pour faire une tâche, peut-être qu'il va garder 2 qui vont travailler avec un logiciel. Après, pour le long terme, malin qui peut le dire. Les biais dans le modèle, est-ce que ce sont des biais des modèles, des biais dans les données? C'est un problème, un double problème, parce qu'il faut déjà les identifier, il faut savoir les identifier, ces biais. Et une fois qu'on les a identifiés, à la rigueur, ça, pourquoi pas, qu'est-ce qu'on en fait? Est-ce qu'on va les corriger, ce qui revient à introduire un biais? Est-ce qu'il faut mobiliser toute la société pour faire une délibération sur ce qui doit être fait? C'est à voir. Et c'est là qu'on peut voir aussi que la problématique de l'intelligence artificielle, c'est quelque chose qui concerne la société tout entière. Donc ça vous concerne tout ça en réalité. Et je pense que j'ai même... Ah bah voilà. Et merci. Pas quelle heure il est. Ah, j'ai tenu. Déjeuner direct? Bon, on va déjeuner. Bah écoutez.
On va revenir.